In today's lecture, we are going to see a very important concept of the chapter Maxima and Minima. And actually, this concept is related to the idea or the concept of points of inflection of a curve or points of inflection of a function. Actually, this point of inflection is defined for a continuous curve. We will learn about these points of inflection in very detail by taking some very important examples. The last example in this lecture you must watch because that is a very important problem which has been asked in a very prestigious examination of India, which is IIT JAM. So watch the complete video, and after watching the complete video we will have a complete idea of the concept of points of inflection. Actually, this points of inflection on a curve is a point where the curve changes concavity. In other words, you can say that it is the point where the curve switches from being concave up to concave down. As you can see, let us see, this is our curve, and this is a point where you can say that x has a particular value, let us say x naught. You can say that this curve which I have shown in this figure, let us say this is AB, this is concave up, and after this point x equal to x naught, if the shape of the curve is like this is concave down, okay, then this point x equal to x naught will be called a point of inflection. In just reverse, you can also think that if there is a curve, let us say this, and at this after this point x equal to x naught, the shape of the curve becomes like this, okay, although this is a continuous curve. So you can see here the concavity is downward of this curve, and for this part the concavity is upward. So a point where the curve changes its concavity from concave up to concave down and concave down to concave up, that is actually called a point of inflection. This is the general concept. But how actually we can find the point of inflection mathematically? So actually you know that whenever you will talk about the point of inflection of a curve, definitely you have to think a particular value of x. You will see that there will be a particular value of x which is called point of inflection, and at that particular value of x, actually the second order derivative of our function vanishes. So you can say in a clear cut manner that if x equal to x naught, this x naught is a particular value of the variable x. If this x equal to x naught is a point of inflection of a continuous curve, let us say f of x, then what will happen? Then the second order derivative, that is f double dash of x, at this particular point x naught will be 0. So this is actually the condition using which you can easily find the point of inflection of a given function. You have only to differentiate the given function 2 times and equate that second order derivative to 0 and solve them. Solving f double dash of x equal to 0, we will obtain the value of x, and that value of x will be called x naught, which is called point of inflection. So it is a very easy concept. What you will actually do, a function will be given to you and you have to differentiate the function 2 times and then equate that second order derivative to 0 and solve the equation. Solving the equation, you will get the value of x, and all those values of x after solving by putting f double dash of x equal to 0 are called the point of inflection. And you can also see how the sign will actually change of this second order derivative at the point of inflection. Actually, there may be two situations. As I have mentioned it here, you can see that if f double dash x naught is 0, okay, since x naught is a point of inflection, so this condition will be valid, okay. And if the sign of f double dash of x changes from positive to negative on passing through x naught, okay, then this point x naught is a point of inflection with the curve going from concave up to concave down, as you can see in this figure. Here this x equal to x naught is a point of inflection. It means at this point f double dash of x naught will be equal to 0, okay. And you can see when you talk about the region where x is less than x naught, then f double dash of x is greater than 0, that is positive, okay, that is the curve is concave up, okay. And in the region x greater than x naught, you will see that f double dash of x will be less than 0, okay, less than 0, that is negative. So the shape of the curve will be concave down. So you can say that at the point of inflection, it is possible that when the sign of this second order derivative will change from positive to negative, then shape of the curve will change from concave up to concave down. And just there will be the reverse condition, that when you can say that the second order derivative will change from negative to positive, then shape will change from concave down to concave up, which I have mentioned in this second point. So this is all about the how we can actually find the point of inflection. The step is very simple. You have only to differentiate two times of the given function, equate that derivative to 0, solve the equation, find the value of x, and all values obtained after substituting f double dash of x equal to 0 will be called the point of inflection of the given function, okay. Now this concept will be very clear to you when you will solve some of the illustrative examples, and I hope you will completely acquainted of the idea of this point of inflection after solution of these illustrative examples. I have actually taken here 3 examples, and as I have told you, the last example will be a question of the which has been asked in the previous year of the IIT JAM examination. So must watch the complete video. Let us see. The first example say, find the point of inflection of the function f of x equal to sine square x. Here our function is sine square x, and it is given that the value of x lies in the closed interval 0 pi. It means x lies between 0 and pi. This is the restriction. So what I have actually instructed you to solve such problems, let us follow all those instructions. Our given function is what? This is fx equal to sine square x. Now to find the point of inflection, you have to find the second order derivative of this function first of all. So we will find first of all the first order derivative. This is f dash of x, and this will be d sine square by dx into d sine by dx, because sine square x you know is a function of function, so it can be differentiated by following the chain rule, and this will be 2 sine x into cos x, that is sine 2x. So f dash of x is sine 2x. Now find the second order derivative. The derivative of sine 2x, you know, this will be 2 cos 2x. So we have obtained that f double dash of x is equal to 2 cos 2x. Okay. Now as I have told you earlier, that if your aim is to find the point of inflection of this very function, what we will do? We will simply equate this f double dash of x equal to 0. So for points of inflection, we will substitute f double dash of x equal to 0. But f double dash of x is 2 cos 2x. So 2 cos 2x is equal to 0. Now since 2 is not 0, so what will be 0? Definitely cos 2x will be 0. And if cos 2x is 0, you know the general value of 2x will be what? That will be n plus half into pi, where n is, 0, 1, 2, 3 and so on. And therefore the general value of x is n plus half into pi by 2. Now let us put the different values of n in this expression. You can see when we will put n equal to 0, x is pi by 4. When you will put n equal to 1, x will be 3 pi by 4. When you will put n equal to 2, that will be 5 pi by 4. And when n is 3, this is 7 pi by 4. And in this way you can obtain all the values of x. But read your question. You are not free to take all values of x, because in our problem it has been defined that x lies between the closed interval 0 and pi. It means the value of x must be between 0 and pi. 0 and pi. And you can see only the first two values, pi by 4 and 3 pi by 4, lies in this interval, because 5 pi by 4, 7 pi by 4 and so on, all are greater than pi. So only pi by 4 and 3 pi by 4 lies between 0 and pi. So we must select only two values. First one is pi by 4 and the second one is 3 pi by 4. And these are the critical points, because we have obtained these values of x after putting f double dash of x equal to 0, and you know that at the points where the second order derivative of the function vanishes, those points are points of inflection. So x equal to pi by 4 and x equal to 3 pi by 4, these are the points of inflection. Okay. Now you can check by the sign scheme. As I have told earlier, that at the point of inflection, the sign of f double dash of x will change from positive to negative and negative to positive. Both are possible. So this is your first point of inflection. This is pi by 4. And this is your second point of inflection. This is 3 pi by 4. Okay. And I have also plotted here this function f double dash of x in against of x to know its sign, that is it is either positive or negative or 0. You can decide from this graph too. You can see as f double dash of x is what? This is 2 cos 2x. So this 2 cos 2x function has been plotted in against of x, and the curve is like this. This is actually the graphical plot of f double dash of x. And you can see at x equal to pi by 4, this function intersects the x-axis. At x equal to 3 pi by 4, it again intersects the x-axis. So at these 2 points, f double dash of x is 0. And you can see when we take x less than pi by 4, this part of the curve, which is actually for x less than pi by 4, this is in positive side. So you can say that this f double dash of x is positive for the region where x is less than pi by 4. Okay. And when you take a value of x which is greater than pi by 4, see the figure. The curve is below this x-axis. It means it is in negative side. And so this becomes negative in this region where actually pi by 4 is less than x, and this is less than 3 pi by 4. In this region, f double dash is negative. You can see. And again, after x greater than 3 pi by 4, you can see the curve is above the x-axis, that is in positive side, and so this f double dash again becomes positive. So you can say that at the first inflection point, the sign of f double dash of x changes from positive to negative. See here, from positive to negative. And you have learnt that if the sign of f double dash of x changes from positive to negative, then the shape of the curve changes from concave down to concave up. Concave, see here, sorry, I have told in a just opposite manner. Concave up to concave down. Okay. Don't see the shape of this curve, because this is not curve of curve f of x. This is graphical plot of f double dash of x. I have plotted it for seeing the sign of f double dash of x. Okay. So at this point, actually the shape of the curve will change from concave up to concave down at this inflection point. But at the second inflection point, 3 pi by 4, situation is just reverse. Here the sign of f double dash of x changes from minus to plus, that is negative to positive. So here actually the page has been turned, but this will be just okay. Let us see here. See. So here actually the shape of the curve will change from concave down to concave up. So I think you have learnt how we actually decide the value of the inflection point and how the shape concavity of the curve changes at the point of inflection. Now let us take another example. This is a very simple example. You can see in this example we have to find the point of inflection of a given function f of x equal to 3x4 minus 4x cube. This is your given function. Follow the same step. What we will do? First of all, we will find the second order derivative of this function, as fx is equal to this much. So f dash of x, you know, this will be what? This will be 12x cube minus 12x square. Take 12 as a common factor, and this will be 12 times x cube minus x square. This is first order derivative. Now, after differentiating this first order derivative with respect to x, you will get the second order derivative, that is f double dash of x, and this will be what? This is 12 times 3x square minus 2x. Now, as you know, at the point of inflection, this second order derivative is 0. So let us equate this f double dash of x equal to 0. And so that you can say that this 12 times 3x square minus 2x equal to 0. Since 12 is a non-zero number, so the second factor will be 0, and take x as a common factor in the second factor. So x times 3x minus 2 equal to 0. And from this you can see the one of the value of x will be 0, and the second value will be obtained by equating 3x minus 2 equal to 0, from which you can obtain x is equal to 3. So you can see there are two inflection point in this example 2. First one is 0 and another is 2 by 3. These are the two inflection points. Okay, how easily we can obtain it, you can see. Now we will see the sign of the function f double dash of x in this case, and you can decide how the shape of the how the concavity of the curve has been changed. See here. Here actually I have marked the two inflection point. First one is x equal to 0 and another is x equal to 2 by 3. Okay. And f double dash of x. What is this f double dash of x? You can see here. F double dash of x I have obtained here. This is 12 times 3x square minus 2x. 12 times 3x square minus 2x. Okay. Now take a value which is less than 0 of x. Let us say, for example, we take x equal to -1 and find the value of f double dash of -1. What will be this? You can see this is 12 into 3 times -1 square, that will be 3, and -2 times -1, this will be +2. And so this is 60, and 60 means greater than 0. So in this region, which is x, where x is less than 0, f double dash of x is positive. I have marked it, you can show, you can see. Okay. Now take another value of x which lies between 0 and 2 by 3, because 2 by 3 is also an inflection point. For example, you can take a value of x which is 1 by 2. This is actually greater than 0 and less than 2 by 3. What will be this? This will be 12 times 3x square, and 1 by 2 square means 1 by 4, so this will be 3 by 4, and minus 2x, since x has been taken 1 by 2, so this will be 1, and you can see this will be minus 1 by 4, that is -3, and -3 means less than 0. So here this f double dash of 1 by 2 will be negative. So you can see I have marked it here, that on passing this x equal to 0 from the region x less than 0 to x greater than 0, the sign of f double dash of x has been changed from positive to negative. Positive to negative. And when this sign changes from positive to negative, you can see that the concavity changes from concave up to concave down. So when you will plot this function, then here concavity change from up to down at this point. And the reverse will be the situation at this point, you can check it. So here this concavity will be up, so you can say that in this, at this inflection point x equal to 2 by 3, the concavity of the curve will change from concave down to concave up at this point. Okay, and you can check it by taking a value of x which is greater than 2 by 3. For example, you can take f double dash of 1. This 1 is greater than 2 by 3, and you can see what will be this. This will be 12 times 3x square. X is 1, so this will be simply 3 minus 2x, this will be 2, and this is 12, and this is greater than 0, that is positive. So I have marked it here, that you can see that f double dash of x when x is greater than 2 by 3 is positive. So I think you have clearly understand what how the problem can be solved. Okay. Now I am taking the second example, which is a very important example, and it has been asked in IIT JAM examination in 2005. Actually, in this problem, you can see we have to find the value of a and b, for which the function f of x equal to x cube plus ax square plus bx has a local minima at x equal to 4 and a point of inflection at x equal to 1. What are given in this problem? Let us see. First of all, understand this problem. In this problem, you have given a function which is defined like this. And in this expression of this function, a and b are not known. And you have to obtain the value of a and b. For obtaining the value of a and b in this problem, two conditions has been mentioned. The first condition is this function f of x has a local minimum value at point x equal to 4. What does it mean? It means when x is equal to 4, then our function f of x has a local minimum value. The another condition mentioned in this problem is what? The another condition is that x equal to 1 is one of the inflection point of this function. Okay, x equal to 1 is inflection point and x equal to 4 is the point of minima. These are the two conditions given in this problem, and then you have to obtain the value of a and b. So we will simply apply the condition of minima and condition of inflection, and then you will see how easily we can obtain the value of a and b. So let us see. This is your function fx equal to x cube plus ax square plus bx. As you know, to apply the condition of minima, we must have to know the first order derivative, and to apply the condition of inflection point, you must know the second order derivative. So let us find f dash of x. You can see the function f dash of x will be what? This will be 3x square plus 2ax plus b, and f double dash of x will be 6x plus 2a. Okay. Now, as in this, when a function fx is minimum, then its first order derivative is equal to 0. You have already learned these things in your previous lecture. In our question, it has been said that when x is equal to 4, then your function is minimum. What does it mean? It means we can equate f dash of 4 is equal to 0. So applying the condition for minima at this point x equal to 4, you can write f dash at x equal to 4 equal to 0. But what is f dash of x? This is 3x square plus 2ax plus b. Now put x equal to 4 in this expression. So this will be 3 into 4 square plus 2a into 4 plus b equal to 0. And this will be 48 plus 8a plus b equal to 0. Now you can see we have obtained one equation containing the unknowns a and b. But as the number of equation is 1 and unknowns are 2, so solution is not possible. So knowing only this equation, you can't evaluate the value of a and b. And so you have to think about the second condition given in your problem. And what is that condition? The question says that x equal to 1 is the point of inflection of this point. And you have learnt that at the point of inflection, if the point of inflection is x naught, then f double dash of x naught is equal to 0. In our problem, this x naught has been given as 1. So you can write as x equal to 1 is the point of inflection, so f double dash of 1 will be equal to 0. And what is f double dash of 1? For this, we will substitute x equal to 1 in the expression for f double dash of x, which is 6x plus 2a. So this will be 6 plus 2a equal to 0, and from where you can see that a will be equal to minus 3. So one of the unknowns has been already known here. The value of a you have obtained is minus 3. Now if you will substitute this value of a, which is minus 3, in this equation 1, you will easily find the value of another unknown b. So let us put a equal to minus 3 in this equation 1. You can see this will be 48 minus 8a, and a is minus 3. So this will be minus 8 into 3 and plus b equal to 0. So b is equal to minus 24. So in this way, we have easily obtained the value of a and b, and you can see that a has been obtained minus 3 and b is minus 24. So how easily we can solve such type of problems if the concept of maxima and minima and the concept of point of inflection is in your mind. I think after these illustrative examples, the concept of point of inflection of a function has been definitely clear to you. Okay, so thank you very much.